welcome once again to Biplab Sanyal. So he finished his PhD in 2000, the year I joined PhD. Okay, and in the same professor. So then he moved to Uppsala as assistant professor in 2003, and he is currently the division head of theory group. He also is currently the director of International's master's program in material science. So he has several awards. I'm not going to read all of them, but what I will tell, which is interesting from the Indian context. So he has been awarded many times for the Swedish Research Links program, okay, which actually funded more than 50 PhD students till that to have an exchange with Uppsala for a longish period of time, like 2-3 months. Okay, and this also helped around 20 faculty exchanges from there. Okay, so in a way, he is helping Indian students a lot for last 20 years. I being the first one. Okay, but also he about his academic accomplishments. He has published 250 papers. Okay, and he is very highly cited, about 10,000 citations and everything. And before I hand it over to him, some fun facts about him. He is a brilliant photographer. Okay, so if you search his name on the Google, you will see his wildlife photography. And he also has a band, okay, music band. Okay, and he is also making short films nowadays. So,
Thank you very much, Mukul, for your kind words. I don't know, it was maybe too much superlative, but it's. I must say that it's always. I feel very nice to come back here, and specifically, I see many students here, so I love to talk and interact with students. So, if you have any question during my talk, just stop me and ask me. We don't understand something. So today. Thank you, Mukul, for this invitation, and thank you other organizers and other members of this Quantum Hub, which is a brilliant initiative, and I hope a lot of good things will be done, which will I will benefit from this, and for sure. I mean, there are many new things I will learn. I'm actively working on two-dimensional materials, so I thought that maybe I can share with you some of the things that I have done in recent past, maybe something from a little bit old times regarding two-dimensional materials. And in all these subtopics, what I will have in common is are the defects. So we know that, I mean, nothing is perfect, ideal, and always defects are there, but defects are not always bad. I mean, they can be used in a good way to tune the properties of materials also. This is something, a strategy that people have been thinking or doing for a long time. I hope you all know about two-dimensional materials. I don't have any much introductory slides. 2004, a landmark year, because graphene was synthesized, a single layer of graphite, by a very simple micromechanical cleavage method. Geim and Novoselov, they managed to do it in Manchester. And since then, it became a sensation. 2010 Nobel Prize was awarded to these people. And since then, we are seeing a boom of a lot of new materials, two-dimensional materials coming in, giving us the possibility of exploring a lot of functionalities. The fundamental advantage of these two-dimensional materials is the huge surface area that we have, and that gives us enormous possibilities to functionalize these surface areas with different chemical objects, to tune the functionalities and to make something which does not happen in the pristine lattice. This is very important. The other important thing is that these two-dimensional materials, they're they're not chemically bonded with each other, so they are so-called van der Waals bonded materials. There's a very weak interaction across the layers. People take this advantage to make some materials like this, which is called van der Waals heterostructures. Then, according to your wish, I have talked to some experimentalists here, and they have assured me that it is possible that you take a 2D material, let's say graphene here, you take another 2D material, you take another 2D material, whatever you wish, you put on top of each other, as you do it in a Lego building procedure like this here. So we can do a Lego building with atomically thin materials with the help of the weak bonding nature across the layers. That's why van der Waals heterostructures, they constitute a big research area, and still this is getting explored heavily. There's a huge scope of research there. And the new addition when it comes to new functionalities, the two-dimensional magnetism, that has made this field even richer. So this is a rather, I would say, a rather new discovery of having a magnetic long-range order at a finite temperature for atomically thin materials, which was fundamentally, it looks like an obstacle according to Marmin-Wagner theorem, but as due to the presence of anisotropy, magnetic anisotropy in these materials, it is possible to stabilize magnetic long-range order at a finite temperature. And this is a very significant development, because now you can have a magnetic long-range order, and if you can manage to have a magnetic material in an atomically thin material at room temperature or above, nothing can be better than that. So that's what people dream of having. That's why lots of research going on in two-dimensional magnetism. I will be talking about that, but before that, I also want to mention something which is also very important for the community, that the photo-induced phenomena in these atomically thin two-dimensional materials. So when you shine light on these two-dimensional materials, because of strong interaction between light and matter in 2D materials, you can observe some very interesting things, specifically regarding the photocatalysis, photovoltaics, and things like that, where we create electrons and holes. And very important question comes whether in what time scales these electrons and holes, they have the possibility to recombine. If we know that, then we can tune our materials accordingly to manipulate that time scale, or even to stop the process of recombination, because at the end of the day we want electrons and holes to move separately, and they give us the desired properties. But for that, a fundamental understanding of recombination dynamics is important, and specifically it becomes important when defects are present, because all these atomically thin materials, we have point defects, even large extended defects are also there. Point defects such as vacancies, interstitials, and some impurities, and all those things, they actually modify the properties of the pristine material. So it's good to know how defects influence the dynamics of recombination between electrons and holes. This is an important thing. There have been very few theoretical studies to understand this, because this is a very difficult problem. In quantum chemistry, people have been doing this for a long time, and there are well-established, very sophisticated methods to do that. But for solid-state systems, it's a very big challenge how to do that. So what I'm going to show here, a method and also an application, which has to be taken with a pinch of salt, because I gave the warning from the beginning that it is a very simple, is based on simple approximations. And if you expect very complicated physics to capture, I mean, that is not going to happen here. That's I want to tell you from the beginning. And I will explain to you what I mean by that. And the other parts is already I started talking on the magnetic order in two-dimensional materials, because as I said that magnetism can be tuned by several ways. You can do a gating with an electric field, or you can do a strain, proximity effects, etc. modifying, yeah, by you can do the tuning of magnetism in this way. You can have some exotic magnetic order. People have reported many complex magnetic order, even spin liquids and things like that. Sometimes superconductivity, there have been reports of two-dimensional superconductivity, and you guys know that a couple of years back we had the bilayer graphene, twisted bilayer graphene showed superconductivity. That became a big news. And specifically, I'm interested in an all two-dimensional spintronic materials where spin orbit torques can be generated, and that can be spin orbit torques can be utilized in magnetization, fast magnetization switching of materials. Conventionally, spin orbit torque is not used. This is a rather new concept. You have a heavy metal, for example, platinum, where it is a non-magnetic material, but it has a strong spin orbit coupling. So charge current to spin current conversion is done inside platinum, and that spin current induces a torque on the magnetization of a magnetic material. So it's a new type of torque, rather new, relatively new type of torque that I'm also interested in, where I am interested in all two-dimensional materials. The spin current generation will be done in one 2D layer, and the magnetization switching will be done in another 2D layer, and that's how the two-dimensional magnetism comes into play. So, so far we have observed some materials which have shown some magnetic order here. So I have been working on this class of systems, FGT. This is interesting because it shows a ferromagnetic order at room temperature. So that's why it is very relevant for the community from an application point of view. But if you read the papers, you will quickly understand that there are many open questions, because as there are many experimentalists here, you can really appreciate that. I mean, while growing the sample, many complex things can happen, vacancies, different defects, some structural issues and things like that, and they are going to influence the magnetic properties also intimately. So there are lots of open questions here. So today I'm going to talk about, I hope I will have time. The first topic is defect-induced recombination dynamics in two-dimensional MOS2 molybdenum disulfide, which is a very well-known, I think the most well-studied compound after graphene. Then this is a rather new work. Raquel, my previous graduate student, she did this work. I think something with molecular magnetism. I've seen Nirmalo is here, so it's for you maybe. Molecular magnetism, how to manipulate molecular magnetism by some defects in a two-dimensional lattice, which is graphene here. It was done by Shumanto, my first PhD student. And then recently we published a paper on this FGT system, which is a monolayer FGT, where we show that there are some peculiar structural reorganizations and the consequence of the structural reorganization in magnetic properties that I'm going to talk about. These are done by these students here. A duo has graduated recently, and this is my current PhD student and my postdoc. So let's start first with the photo-induced phenomenon that we are talking about recombination dynamics, or in other sense, we are talking about how a state decays with time, how the population of a state decays with time. Let's put it in this way. I will tell you what I mean by that. The actual problem, if you want to study this problem, you need to study a time-dependent Schrödinger equation, where you have two degrees of freedom, different degrees of freedom, ionic degrees of freedom and electronic degrees of freedom. We all know in textbooks that whenever we are given this problem, we immediately understand that ions are much heavier objects than electrons. So we can decouple these two degrees of freedom by the so-called Born-Oppenheimer approximation. And we can make our dynamics based on Born-Oppenheimer approximation, where usually what is done here, so you have a potential energy surface, you have the energy, you have the reaction coordinates here, you have a potential energy surface which is provided by the ground state of the system, and that is found out quantum mechanically by solving an electronic problem only. What we usually do, we do molecular dynamics simulations by treating the ions as classical objects, but these ions move in the potential energy surface created by electrons. That is purely quantum mechanical, whereas the ionic motion is driven by Newton's second law of motion, which is purely classical. So we do, or most all the things that you see around, they're based on molecular dynamics simulations based on Born-Oppenheimer approximation, that we have a ground state potential energy surface and the ions move there. Like this, so they move in the potential energy surface. So basically, then we say that we neglect all non-adiabatic effects. In simple words, it means the coupling between electrons and ions. They are all neglected in Born-Oppenheimer approximation. But if you want to go beyond Born-Oppenheimer approximation, because we are going to study some systems where electronic and ionic degrees of freedom, they're coupled with each other. We can no longer decouple them. For that, we need to go beyond Born-Oppenheimer approximation. And there, the two standard ways of doing is that so-called, I'm not going into any detail to bore you, but these are Ehrenfest dynamics and surface hopping approach. So in simple words, Ehrenfest dynamics tells you that the system moves on an average potential energy surface. So there are many potential energy surfaces you create, and then you define an average potential energy surface, the ions move there. And in the other approach that I'm going to use in my research, which is called a surface hopping approach. Here in this approach, you have the ground state potential energy surface as well as many excited potential energy surfaces. And when the potential energy surfaces are very close to each other, the electrons hop from one potential energy surface to the other. That means there is a coupling that is established between these potential energy surfaces. That's why it is called a surface hopping approach. So all I need to understand or calculate from here, what are these non-adiabatic couplings? What are these couplings? What is the strength of this coupling whenever this situation happens, and that one you can go switch from one potential energy surface to the other potential energy surface. So there's a flow chart here which is shown. You start from a real many body problem where electrons and ions are simultaneous. Yes, please.
What is the typical scale of this energy with respect to KT on the right?
I will show you some numbers. Yes. Here, that's a good question, but here I will talk about room temperature only. And in room temperature, we can expect, it depends on the material characterization also, that electron phonon coupling and all these things. It depends on how much the phononic degrees of freedom are coupled to the electronic degrees of freedom. I would say this is more of a materials issue problem. But for MOS2, it has been shown that there is a more or less significant electron phonon coupling, which can give rise to, which can qualify for this method that electrons and ions are coupled to each other. So basically, you start from the absolute quantum many-body problem. Then if you have a quantum ions, that if you want to study ions quantum mechanically fully, then you have some methods which are mostly used in quantum chemistry, like a multiple spawning methods, but it's a very difficult method for solid state problems. So I'm not going to take that route. I take this route here. We want to consider non-adiabatic effects, but then I want to go to a method called surface hopping, which is more technically called fewest switches surface hopping method. And then I will study the non-adiabatic effects. Now, the point is that still is a highly non-trivial problem, because I have to have different potential energy surfaces, because you come with photons, you excite electrons, and you put them to the empty states. And now immediately you realize that there is an electron hole coupling that you need to consider, which is itself a very complex problem. How to consider electron hole coupling? So that means we are no longer talking about a single particle picture, but two particle picture. Ideally, I must do that. Where all this exciton physics and everything comes in with bound electron hole pair and things like that. But I'm not going to do that. That's why I'm saying that it is a very simplistic approach. I will still stay in a single particle level. That means I will use the so-called standard cone sham in our language, solving a cone sham problem. I will still do that, like how you do normal density functional calculations. I will be there in that regime. But if you are a critic, you can very easily criticize me, saying that this is too simplistic because the electron and hole, they are interacting with each other, and this is a many-body Coulombic interaction, so it is very complex. You must take into account. I will completely agree to that, but still, I don't have the mechanism to do that for a solid-state system. So I will stay with a single particle picture. Yeah.
So if you do a BSc, it is that would be completely difficult. But can you not put a term here, which is more of a hydrogenic term for electron holes? Classical looking potential.
Maybe that can be tried, but I think a better approach would be to actually create the excitations in this way, which is called a delta SCF method. So you still do a cone-sham problem, but now you take the electrons and put it in the excited states, that means unoccupied states, and do it self-consistently. This is one of the ways to do, or you have to do a time-dependent DFT problem, which is still difficult for solids. So that's why I did not take that into account. What you do actually, you create your trajectory by normal Born-Oppenheimer molecular dynamics simulation, and for every trajectory point, you solve this cone-sham equation by placing the electrons in some of the unoccupied states, like an active space calculation in quantum chemistry. We want to make an analogy with that.
How
Yes.
much error would be introduced by neglecting Coulomb infection?
That is it's a very good question, but I don't know how to answer this, because for that either you need a reference calculation or you need extremely good experimental study. By extremely good experimental study to give me the dynamics, the time of recombination via different pathways, which is, I think, is impossible to find out. MOS2, we had a hard time to find out experiments for real good material quality where we have almost no defects in the system. So
It was working.
I just came here.
Do you need to do anything?
he cannot forget that he is an experimentalist. No, I think it is just overlapping with something here. I lowered this thing. It could be a feedback there. So it depends on wherever I am going. Okay. It's a site dependent problem. Okay.
I just went there and then.
So, but as I said, that it depends on what level of sophistication you want. But I told you the challenge is that either you have a very high quality reference calculation to estimate the error, or you should have a systematic experimental study from which you can get the time for this recombination dynamics, and then you can compare. So we faced a problem with that because we did not get things like that. Okay, so just one equation slide. We want to study this time-dependent Schrodinger equation where, the electronic part is also related to the ionic motion, and the capital R is the ionic variable, small r is the electronic variable. So what we do, we expand the electronic wave function in terms of the adiabatic basis. Adiabatic basis means this is the normal cone-sham equation where we take the implicit dependence on the ions. That means given the ionic position, we just calculate the electronic structure problem. But if you you know that you have the expansion coefficient C's here. So if you expand this equation, you get a matrix like this, where the off diagonal elements are defining the non-adiabatic couplings. Let me show you the picture, then you'll see that. So these are the non-adiabatic couplings. That means you have the single particle states, Kohn-Sham states phi j and phi k at different times, and then you calculate this matrix element, and that gives you the strength of the non-adiabatic coupling. In other words, whenever these two potential energy surfaces are coming close to each other, you try to measure the coupling strength between these two surfaces, so that you can estimate how much this non-adiabatic coupling can be. And whenever you get these non-adiabatic couplings, you can do some kind of Monte Carlo stochastic method simulation, which is called the surface hopping method. And then you find out the population of states, that at different times, what will be the population of a particular state. In other words, let's take an example that I have a valence band maximum in my semiconductor. Molybdenum disulfide is a semiconductor. I have a conduction band minimum. I put my electron in my conduction band minimum, and I have a hole here. I don't care about the hole, but I care about how with time the population of this excited state is changing. What is the temporal behavior of the population of this excited state? From there, I can have an exponential fitting with that, and I can get the time scale of recombination. That is how we extract the numbers. If I now come to the exact example of this, so basically MOS2, if you don't know about MOS2, it's a two-dimensional material. We have 3 atomic layers. This is a side view. You can see that these are molybdenum atoms, and on top and below we have sulfur atoms. But this is one monolayer of MOS2 with 3 atomic layers. And we can expect also from experiments, it is shown that there are 2 types of defects. One is a vacancy, sulfur vacancy, that happens very commonly, and you can also have some sulfur adatoms, or you can call it interstitial or adatoms, it does not matter. So you have some sulfur adatoms on the top of the sulfur layer. Besides this, you can also have other types of defects, for example, a vacancy at a molybdenum site or an interstitial molybdenum atom. These are some of the defects which are less probable to form. How do we know that? Because in previously we have calculated the defect formation energies. That means how much energy is required to form the defects. Lowered the energies, more probable to form those defects. And if you look into this one, so that you see the lowest formation energy on the y-axis is formation energy for MOS2. If the lowest formation energy happening for the adatom or the interstitial on top, and then comes the sulfur vacancy. So, and then comes other types of defects. So we thought to study a bunch of defects to see that how the recombination looks like.
You are taking this route of calculation just because you want to study defects, and there you need to assume a lot of atoms into that. That's the reason, right?
The motivation of the study is to find out that what defects do in the dynamics here. So
because a lot of students may understand that MOS2 can be very well be studied by time dependent thing or like BSc calculations. It is a defect free.
Right, but I'm talking about in the time domain. Actually, I will be talking about time, and I will show you that is an important factor. Actually, that's the speciality of this. I will show you. But just to make a electronic structure perspective of this, so this is the energy level diagram. You have the pristine MOS2 where you have a valence band maximum and a conduction band minimum. Red means it's occupied and green means it's unoccupied state. And then you have different vacancy structures, and you see that how different defect levels they form in the gap. So this is important to realize, because when an excited electron comes down to its ground state, it either can come down directly, which is called a direct recombination, or it can come down via all these defect states which are called trap states. and any defect state which is close to here, this is a hole state, hole trap we call it, and these are electron traps which call it, which are close to the conduction band minimum. So the recombination will work in this way, either a direct recombination or via different defect states, trap states. And for that you need to have a little bit of understanding about what are these eigenvalues, what are and what type of orbital characters do they have, because all we are talking about, if you remember the formula, that non-adiabatic coupling is a matrix element that we are calculating across single particle states. So the character of those states, the orbital character of those states, these are also important information. For example, we see that for pristine we have different types of, I don't know whether you can see that here, different types of d orbital symmetries can be seen for different symmetries for the conduction, for valence band maximum and conduction band minimum, either in plane or out of plane d orbital symmetries you see. Sometimes these are important to understand these transitions actually. Anyway, let's come to the actual point here. I have the pictures of two scenario here, two scenarios. One is the interstitial or the adatom case. You have the valence band maximum, you have the conduction band minimum, and according to your calculation we have a defect state which is a hole trap state here. So you can have one pathway where the electron jumps directly to here, which is a direct recombination, and the other one that it comes from the valence conduction band minimum to this trap state, and from the trap state it comes back to the valence band maximum. So if we calculate the time of recombination, this is what Mukul was, the important thing is about the time of recombination. And for a pristine we have only one possibility, a direct transition will happen. This is of the order of 70 nanoseconds, that according to our calculation, which matches more or less with one experimental result where we found with a lot of struggle that any material which they claim that they have a very good quality MOS2 without defects. Otherwise pristine, how do we get pristine samples? So we matched with them. So more or less 70 nanoseconds is okay with them. Now for the interstitial sulfur, we have a hole trap state here. So you have still a direct recombination here. Now the time scale of recombination has changed drastically to around 21 nanosecond. So not only the recombination times through the defect states are important, but also direct recombination times are also getting affected because of the presence of defects. That means these defect states, they are also affecting the conduction, the direct recombination times. And similarly for sulfur vacancy, you have two such defect states. One is a trap state, hole trap, and one is an electron trap, and you can define many different recombination pathways and their corresponding times. Yes, please.
Do your calculations involve both radiative and non-radiative components by calculating power?
These are all. This is a very good question. I forgot to mention. These are non-radiative.
But what if radiative component dominates something?
Yeah, then you have to go to a different method, because this method can actually take care of. So that's why I say that this is the other Ehrenfest dynamics. If I take that method, that can take care of that one. So this is a non-radiative method.
70 nanoseconds.
Yes.
From photoluminescence, I mean, we do not know if this is radiative or non-radiative.
Right.
In principle, it's related to radiative because we are seeing the light out.
Right. So you have to, but there must be other experiments where you can probe the non-radiative processes also, right? Difficult, yeah. So there lies actually a little bit of limitation also. We must have, the problem is that we must have a method which can take care of both of them. So this does not exist. So that's a limitation. But anyway, then I'm not going into any such detail, but if you look into the summary of the fastest pathways, fastest means the most probable recombination pathways. So we have the hole trap for the interstitial sulfur, we have the electron trap for the sulfur vacancy, and likewise for other types of defects, we can identify the fastest pathways of recombination from all these time scales that we have calculated. One thing that we understand is that whenever defects are present, the recombination is accelerated. That means the recombination happens in a much faster time scale, which I think is already understood and well known, and that is qualitatively that we can find here. Okay, so this is all about some recombination dynamics in defected two-dimensional MOS2. Now, very quickly, I want to show a very old study. Now, I'm coming back to magnetism once again. The old study of some molecular magnetism. And there we did some interesting computer experiments. Real experiments do not exist, and I could not convince anyone to do it. So, this is all about manipulation of the spin states of magnetic molecules. Nirmal, do you know about all this? You have worked on this, but this thing we were thinking that whether we can find out yet another way to manipulate spin state, and there we thought to use the substrates to manipulate the spin state of a magnetic molecule. And that magnetic molecule which is used here is iron porphyrin, where iron atom is at the center, which carries the magnetic moment, and it's surrounded by nitrogen atoms and carbon atoms. Incidentally, iron porphyrin is a part of hemoglobin that carries oxygen in our blood. So that's why it has many different applications, different perspectives. But here, the perspective is the change of the or the manipulation of the spin state. What happens is that here, that iron is in a +2 charge state. That is, it has 6 d electrons, and 6 d electrons means it can exist in different spin states, 0, 1 or 2. It can completely, magnetic moment can be completely quenched, or it can have an intermediate spin state S equal to 1, which should give rise to a 2 Bohr magneton, or it can have a high spin state where we expect a 4 Bohr magneton, magnetic moment for iron. Now, the question is that can we switch between different spin states by doing something? And this is a calculation of the total energy as a function of the value of the magnetic moment of the molecule. You see that clearly, you see that there are two minima here. One is the ground state, lower in energy. The other one is a little bit higher up in energy. The ground state happens for S equal to 1 spin solution. That means 2 Bohr magneton magnetic moment. And this one happens for S equal to 2 spin solution. And this is observed. Why this is observed? Because of the iron nitrogen bond length. Iron is surrounded by 4 nitrogen atoms. Whenever the iron nitrogen bond length is below 2 angstrom, you get a low spin or intermediate spin state. When it is bigger than that one, you get a high spin state. So the question is that can we somehow utilize this information and do something with the help of a substrate? So we did this. This is a purely numerical experiment that I am going to show you. So what we did is that you take a graphene lattice, which is a 2-dimensional lattice, and we know that if you create some vacancies in graphene lattice, that becomes a trapping center. This we have seen in many other cases, that if you have some objects, they will be trapped in at those vacancy sites. So if you have a magnetic molecule sitting on top of a graphene lattice with a defect there, it will be trapped on the defect site. But of course, this is not chemisorption, this is physisorption. That means there is no chemical bond between them. Now, what you do in this native state, what you find that the magnetic moment of iron has a value S equal to 1, and it is out of plane. So it is like this. Now, what you do, you apply a strain, a tensile strain in the graphene lattice on the substrate. Somehow the same tensile strain is transmitted to the molecule, and the molecular spin state is changed from S equal to 1 to S equal to 2. And the easy axis of magnetization, that means it was out of plane before, it becomes in plane. And then you apply a compressive strain, then it goes back to the S equal to 1 spin state and it goes back to its initial state. So that basically means if you can somehow mechanically manipulate the substrate with, of course, you need some defect sites, then it can change the spin state of the molecule in an indirect matter. The physics is still the same. Whenever this tensile or compressive strain is applied, the molecule gets affected, and there then iron nitrogen bond length gets affected. So so when it expands, you get a high spin solution. When it comes back below 2 angstrom, it gets a low spin solution. And that is easily understandable from your electronic structure or the occupation of the orbital studies. You see that you have an occupation in the normal state which has 4 electrons in one spin channel, 2 electrons in the other spin channel. But when you do the tensile strain, then you have the distribution of 6 electrons becomes 5 in one spin channel and 1 in the other spin channel. So we understand all these things, and the question is how to detect the spin state, so which is a important thing. Yes.
Speaking of the spin,
Yeah.
this equatorial plane, is it dependent upon the rate at which you stretch the layer, or it's like
Purely electronic structure effect.
so it's a DC effect? When you stretch it, there is no dynamic.
There is no dynamics here. There is no dynamics. It's you stretch it, and there is a change in the electronic structure of the molecule, not of the base, of the molecule. The molecule actually, if I show it the next slide, you will understand that. It's a little bit complicated theoretical slide anyway.
Is it because of van der Waals coupling between
No.
plane and your graphene sheet, or
No, I mean, somehow the strain is transmitted to the molecule, and that is happening via the very weak interaction between the molecule and the substrate. But the change in the spin state, like the easy axis of magnetization, whether it is out of plane or in plane, that is critically dependent on the resulting electronic structure, what is happening. Yes.
Graphene is basically serving as a stretching membrane.
Exactly.
So if you can apply the strain by some other means, you will see the same effect. Or this vacancy in graphene will have some effect.
No, the vacancy in graphene is important, because if you have a absolutely pure graphene, the effect will not be there. So you have some asymmetry created in the lattice by this vacancy, and that helps to transmit the strain to the molecule. Also, it helps as a trapping site of the molecule. Otherwise, the molecule will be moving. Yeah.
We can perform experimental precision molecule, say by using FriQuant Seminar Series.
Yes.
We apply strain on that molecule.
Directly. The same thing will happen.
We'll see the same.
Absolutely. All thing boils down to the iron nitrogen bond length. Yes, and the corresponding electronic structure changes. Your question about out of plane magnetization to in plane magnetization, this is critically dependent on the electronic structure what we have, that which d levels are occupied because of this. And these occupancy of d levels are different for unstrained state and the strained state. That can be very easily shown by calculation.
Things are increasing in all sides, or it has a particular.
It's an isotropic thing. At least in our calculation, it's an isotropic, but maybe you can devise something that.
If you kind of apply compressive strain from the perpendicular side, you will see the same. So it's probably not.
That I don't know. That I cannot tell, because it was done in the lateral plane. All you need to do is to change the iron nitrogen bond length in the plane of the molecule. That you need to have. Yes, you had a question. Yeah.
This compression is from this equilibrium, or it's just whatever effect we have applied, we are just like taking that manner.
I think so. You can think it like that. So in the strained state to an unstrained state, if you bring it back by applying a compressive strain, it will give back to the initial state.
But if we can like decrease, like compress it down, like the strain, we can compress it further, right, from the equilibrium condition. That
If you compress it further, I don't think the spin state change will happen. No, I don't think it will stay in the normal state actually, which is S equal to 1. That I believe that will happen. But you know, I mean, there is a catch here. I mean, experimentally, if you want to design this, I don't know, you have to have a mechanism of tensile and compressive strain. Maybe it is still possible by putting graphene on some kind of membrane and then stretching that membrane like that. So far, I have talked to many people. I mean, it's a very complicated experiment to realize that's unfortunately.
There will be lattice mismatch between the graphene and the molecule. That strain will be there. Unless it is.
If you don't do any extra strain, if you keep it like that, so the spin state of the molecule is in its native state. So nothing, even there is an interaction, nothing happens to the molecule. So you really have to strain the substrate in order to get a spin state change in the molecule.
So how much strain do you need?
A very small, 1 or 2% strain. Because we are talking about a subtle change in iron nitrogen bond length, very subtle change that can happen.
So something other than graphene, what? I mean, why use graphene and then stretch it by 2%?
It's a work of 2011. That time, just Nobel Prize was given to graphene. There's a very trivial answer, but graphene at that time, everybody was working on graphene. So we thought about one single layer material, but maybe something else can be tried. We did not pursue any generalization of this.
More of a generic thing.
Could be, it could be, yeah, translate, the strain has to be translated so that the iron nitrogen bond length can be affected, and then the resulting thing. Yes, please. Void dimension, the vacancy. That's a good question. I never looked into that, but it's a very small strain. You know, we're talking about 1 to 2% strain. So the voids, maybe there is a subtle change in the electronic structure, maybe in the density of states. I don't know the quantitative answer to that how much it changes, but it is I would expect a subtle change, not any important change there, because our idea was not into looking into the void in the lattice so much. Its effect on the molecule was our primary interest. So we looked into that. I think I have to move faster. This is if you are interested and if you want to talk about it, please contact me later on. Old paper that wasn't. But now the new paper, I want to really talk about this. Maybe this becomes interesting for some of you. The FGT, the iron-based two-dimensional magnets, Fe5GTE2. So there are some bulk studies in experiments, and still till today there is no monolayer of this material. These are van der Waals magnets from bulk. When I was discussing in the morning, I understood that it is not always trivial to get a monolayer from any van der Waals system. So there are some issues there. Nevertheless, this is iron-based system. It has magnetic properties, and some experiments they have many experiments they have who have done magnetic measurements. They have shown that there is a magnetic order at room temperature. That's why this material becomes important. So now we wanted to study this material, and like in any other magnetic material, we go through some of the procedures. And one important thing for us to understand that how the magnetic moments couple with each other magnetically, whether there is a ferromagnetic coupling or antiferromagnetic coupling, and how this coupling varies with distance between the pair of magnetic moments. This is a very important thing to understand the exchange procedure, and finally, obviously, to calculate the magnetic transition temperature and all these things, those things. So there are well-defined methods for studying these things. But also an important thing that these iron atoms, this is a low-dimensional system, and iron has d electrons. And these are supposed to be correlated electrons. Now, when it comes to correlated electrons, we really do not know that how strongly correlated these materials are. Here, the experimentalists can help us from their experiments to give us some idea of telling us whether this is from some photo emission experiments, whether these are strongly correlated or not so strongly correlated, something like that. In literature, people have even tried to estimate the value of so-called Hubbard U, which is used to describe this kind of electron correlations. So we don't have the possibility here. So we have to calculate it from ab initio the U values. So we try to calculate also the U values, Hubbard U values for different iron atoms. There are methods to do that. So there are several layers of this problem, and which is a generic thing. But another thing I must tell you, that as this is a two-dimensional magnetism, I told in the beginning that you need to break the symmetry of the model. So any isotropic Heisenberg model cannot give you any magnetic long-range order according to Marmin-Wagner theorem. So you need to have the presence of magnetic anisotropy that breaks this symmetry. So that means a calculation of magnetocrystalline anisotropy is a must for two-dimensional systems. You need to do that. There is also a standard procedure people know for ages. You have to turn on spin orbit coupling and you do this calculation. So that is an input for our finite temperature Monte Carlo simulations, and also the exchange interactions. These are input. About these materials themselves, so these are taken from experimental papers. This is the family Fe(n-x)Ge(Te2), where n is 3, 4, and 5, and x minus x means there are always some iron atoms missing from this system. Some vacancies are there. These are all metallic ferromagnetic systems. You see that these are iron atoms. This is Fe3 system, iron atoms. The outermost layers, these are tellurium atoms, and you have some germanium atoms here. So actually, for n equal to 3, people could manage to produce a monolayer, which gives you 130 Kelvin around the Curie temperature, and in bulk this is around 200 Kelvin. For n equal to 5, where I have done my study, there the Tc is around room temperature. And there you see, this is the interesting thing to see, that you have the tellurium atoms as outermost atoms, and then you have one site which is we called iron 1 site, which has an equivalent site here in the bottom. That's why we called iron 1A and iron 1B. And experimentally, people have observed that there are partial occupations in both sites, whereas the other iron sites, they are fully occupied. Okay, so now this is a new thing for us, that we have one particular site which is iron 1, I call it. They have the possibility of occupation in the upper side or a lower side. So now I use a nomenclature called U or D to define my structure. Equivalent positions, but there is a partial occupation that is seen in experiments. When they do XRD and all those things, they find partial occupations. Yes, please. These are all experiments are done for bulk systems. But remember, these are van der Waals coupled layers. So what we have tested something, and then we thought that to do all these calculations in bulk is a little bit non-trivial. So we have taken a two-dimensional form of it, a monolayer, and we think that the monolayer, the characteristics in the monolayer, they will represent the characteristics of bulk, because the interaction across the layers is rather weak. Yes, please. It's not so easy question. So now this is, first of all, this partial occupation is one thing. The other thing is the magnetization data as a function of temperature. This is very weird, and this we do not understand why it is at low temperature. You see a low magnetization value, and then you see some dips and you see some peaks here, and finally you have a ferromagnetic to paramagnetic phase transition. The normal phase transition happens. So it's still a mystery that what happens at a low temperature, why the magnetization is so low. So some papers say very hand wavingly that it is not a there is a very complex magnetic order present at low temperature. some helimagnetic order, some people have said, but there is no direct evidence of that. And so we tried to reproduce this and we failed. We didn't get this behavior because you need very frustrated magnetism, a picture of frustrated magnetism at low temperature in order to reproduce that. So far we could not, nobody could find out this one. There is one
bulk contraction or something.
not this system. Maybe there is something for Fe. Fe3 is relatively simpler, and there Fe5 is new system. Fe5 is rather new system, and very less studies are there. Maybe somebody will do that, but because of this structural rearrangement, I think there are lots of issues there. What happens? So now I will define two structural models. One is that one Fe1. Remember this Fe1 species. Okay. There's something else I have to tell also. Some experiments from their STM studies, they claim that they see some superstructure. So the unit cell is not a 1x1 cell that I showed you, but it's a √3x√3 superstructure rotated by 30 degrees. It basically means that in every layer in the unit cell, you can think of 3 iron atoms because it's √3x√3, 3 iron atoms. And then based on that superstructure, we define two structural models. One is that iron 1, which must have 3 atoms. In one structural model, they are all in the upper layer. We call it UUU, that all the 3 iron atoms in the upper layer. And in the other structural model, we have a UDU. That means 2 are in the up position and 1 is in the equivalent down position. You remember this Fe1A and Fe1B site? So we do like that. So energetically, the UDU structure, that is energetically favorable. That means we cannot expect this UUU structure to become stable. So there will be always some iron atoms in the lower position. Now, how much it will be there and how they reach there, this is still an open question. But at least what we find out that these iron atoms, that Fe1 site is very prone to form vacancies, that they don't like to sit there. They really can easily be detached from their site, and the diffusion barrier going to its immediate iron site is rather low. So from there we can understand that maybe that iron atom detaches and it is diffusive in the system in the initial growth process when the synthesis is done at a high temperature and things like that. But once again, I want to emphasize here that these are our hypotheses, and there is no direct proof there, because experimentally nothing is known what happens during the synthesis. But the resulting STM simulations for the UDU and UUU structure, the UDU structure more or less reproduces the experimental result. If you look at it very carefully, you will see that these are almost like circles. Here, these are bright tellurium states that you see, where these are kind of oblates, the tellurium atoms, and this is happening because there is a trimerization of tellurium atoms happening on the top of the surface. That's why the STM looks a bit distorted, and that is what is seen in experiment. So from there we can conclude that a √3x√3 superstructure is actually a good model, a structural model to study this.
That is something like a charge density order.
It is, well, I don't know. There is no charge density still. But there is a trimerization, because you remember that one of the iron atoms has moved from its position to the down position, and that affects the lattice as well as therefore the tellurium atoms come together and make a trimer. And this kind of distorted, these white blobs, they happen because of this trimerization of tellurium atoms. So it's a consequence of the UDU structure. That is what we want to emphasize. So now when we have a structural model like that, we go forward, we go ahead and calculate the magnetic exchange interactions among all these iron species and see what we get. And this is a very busy plot. I will just take you through this. So there is a formula for calculating interatomic exchange interaction, well-established formula. As a function of distance, you can calculate quite precisely, I would say. It cannot be direct exchange all the time. don't know what type of exchange mechanism still, but we can calculate the numbers and we can calculate the strength and the numbers that we know. But the mechanism of exchange interaction is highly non-trivial to understand. Some people say that it is RKKY, but it is modified RKKY also. So metallic systems, these are usually RKKY interactions. So I also believe that there is RKKY, but it could be a mixture of other short range interactions and RKKY also. So now the important thing is that if we find out a combination of ferromagnetic and antiferromagnetic interactions, and there the frustration in exchange comes actually. And whenever we see the coexistence of these interactions, we jump in joy, and then we can say that, okay, here. So for example, so here what is plotted is the central atom is an iron 1U atom, and we calculate the pair exchange with all other iron atoms and also with itself in the same plane. So more or less you see that there are some antiferromagnetic components happening here, and mostly the strong antiferromagnetic components are coming from iron 1U interacting with iron 1U in the same plane. So there is some kind of antiferromagnetic interaction, and there is a coexistence of other ferromagnetic interactions. This we see whenever our central site is Fe1U. When our central site is like the number 5 normal iron atom, we do not see much existence of antiferromagnetic interaction. So that first the iron 1 species is rather special. It provides us some antiferromagnetic components which can give rise to some complicated magnetic order at low temperature. So then we start taking into all these things into account. We do Monte Carlo simulations, and then we produce a sublattice magnetization as a function of temperature. These kind of plots are usually not seen so regularly, but nevertheless we can do that. So different curves, they represent the sublattices, how the magnetization in those sublattices behave as a function of time. So you see that different types of magnetic atoms here, they behave like this, and then the iron 1U, the one in the upper position, that their behavior is a little bit different here. The M versus T behavior is a little bit different, and this happens because of this coexistence of ferromagnetic and antiferromagnetic interactions.
Same temperature.
So one single transition temperature is there. Now coming back to your question, that if these are done in the normal DFT level, which gives a very high estimation of the cool temperature, which is around 500 Kelvin. In experiment, this is around 300 Kelvin. Some people have claimed that if you use Hubbard U correction in the DFT plus U scheme, you can do better, but we completely disagree with them. And there is a new paper that we are writing where we show that if you use dynamical mean field theory, then you get almost the same number as the experiment. So our conclusion is that DFT is okayish just for trend. DFT plus U is not, and DFT plus DMFT, dynamical mean field theory, is the method to study these systems where electron correlations are like a strongly correlated metals. So what is used for, that is ideal for this. But you know, this is a very complicated methodology. But we managed to do that systematically for Fe3, Fe4, and Fe5 system that we are writing in another paper where it will come out. And you will see that that reproduces very nicely, because that renormalizes these exchange interactions. And as a whole, it renormalizes the TC to a lower value. So you get around 200 something as a TC. I'm sure it does more than that, but for that we need some experimental results of photoelectron spectroscopy. Some kind of photoemission spectroscopy we need.
So more iron. Right. The lowest.
This is a very complicated question you are asking. So we can expect from a naive point of view, Fe3, Fe4, Fe5, we should have a trend. But some experiments, it's difficult to get a trend because of the amount of iron vacancies present in the system. It all depends on what sample you have. So ideally, you want to see one experimental group studies Fe3, Fe4, Fe5 in a similar way, and you get a linear trend or non-linear trend. I don't know, you see a trend. different samples have different characteristic features, and that's why we are in a mess right now. Fe3 is a little bit better studied, but Fe5 is very poorly studied, and these things opens up a lot of questions now. So we really need very systematic studies. Anyway, I mean, the final thing is that you see, if you plot the canting angle, so for every sublattice we can extract the average canting angle, and we see with respect to the global z axis, and we see that for Fe1U, which has a peculiar magnetization data here, it has a much larger canting angle around 40 degrees, whereas other sublattices, they have much lower canting angle around 10 degrees. So that means that particular iron species, they are largely deviated from the global z axis. So it gives rise to, it can give us some hints about very complicated non-collinear magnetism, but still with that data, we are not able to reproduce that peculiar M versus T plot. So that means there is much more which you are missing here. This is a ferromagnetic metal, but individual sublattice moments, they have different canting angles from the global z axis. This is rare. This is some kind of canted ferromagnet, you can say. It has to be some rare kind of magnetic ordering present here. Otherwise, I mean, the M versus T will not show you that behavior. The spontaneous magnetization is rather low actually at low temperature. So that's a good question. But here we have a monolayer. So we don't have, okay, those things will be taken care of. If you see, it's rather difficult to calculate for bulk because you need to have your unit cell becomes big and you need to have 3 layers and things like that. But we are also doing that, and we can find some peculiar features, and we can see that we can reproduce the experimental results. At least the TC we can reproduce. Sometimes very peculiar antiferromagnetic interactions happening across the layers also.
Show the sign of frustration, but not the simulated one. Like you see a big analyze could be.
If someone can do that experiment, that I don't know. I mean, it's difficult. I am sure it's very difficult.
Dysprosium, holmium. Many of them have a ferromagnetic transition, but on lowering it down, they have a bunch of.
That is exactly some experimental groups they have talked about. Now here there is a delicate competition between the magnetocrystalline and anisotropy, which wants all the moments to align along the z axis. But there is also frustration in exchange that doesn't allow it to do that. So that's why the resulting moment is a canted solution from the global z axis. Now also we have to remember one thing, that we have neglected completely more complicated magnetic interactions here. For example, Zaloshinsky-Moria interactions are not included here. Maybe some higher order interactions. Many things can be included. So we have also calculated Zaloshinsky-Moria parameters, but these are coming in the next paper. So yeah, here we don't have that. So that can be important because the origin of skyrmions in these magnetic systems, that is also very undefined. From where the skyrmions come, this is not clear. Some people say because of iron vacancies, iron interstitials, oxidation of iron. There are many different viewpoints. So that's why it is important to study that also. Experimentally, absolutely. Experimentally, one of the recent papers, they claim that it is happening because of iron atoms and in the interstitial, in the van der Waals gap. That gives rise to skyrmionic features. That was a bulk study. Most of the things are bulk. This is Fe3. I'm talking about Fe3 system, where usually people did not talk about vacancies so much, but now people are slowly discovering that these vacancies can have very profound effects on complicated magnetism. So now they're jumping into that field. Anyway, I need to finish it here. So what I want to say, if I do a grand summary, So then the first part I showed that how one can study in a very simplified way non-adiabatic molecular dynamics simulations to show the recombination dynamics, and I had an example of 2D MOS2 in presence of different defects. And in the middle part, I talked about how you can manipulate the magnetism of a magnetic molecule indirectly via some substrate effects. And finally, I talked about how iron vacancies and their diffusion can give rise to a peculiar structural form, and which has some critical consequences on the magnetic properties, exchange interactions and magnetic properties. If you're interested, you can go through these papers and you can ask me later on.
Yeah, so it brings me back to MOS. So essentially, radiative recombination times of all these 4 or 5 materials are sort of well known. They are on the order of a few hundred femtoseconds at low temperatures.
For these 2D materials.
So maybe this information can somehow find some place in your theory to.
Is that in presence of defects, or how are the samples?
Samples would be defective, but in the end, these are radiative recombination times, which are intrinsic properties of the 2D system. Because I mean, many people have reported that they have reached homogeneous limits materials by HBN encapsulation, and then these times are on that order.
Okay.
Or what if they have a very, very local probe? If you have a very, very local probe, then you might not be hitting the defects, right? That may also happen.
Yeah, but how do we measure the recombination time?
I'm saying that if the experiment is done by exciting very locally.
When you come with a photon light, it has a light of
Micron, but still
it's a huge area of excitation, so it's not locally cannot be done. Yeah, it's but I will look into that. Maybe I can discuss with you regarding some experiments. Yes, please.
There is one sample like this, there should something that charge neutrality or something like that, which is causing ice cycle system.
Can you talk about metallic systems? Maybe this is a question to the experimentalists mostly. I mean, who do high temperature synthesis of materials like that? I mean, one thing from our kind of calculations, we can see that the probability of formation of that particular species of iron is very high, probability of vacancy formation, and that must be somehow related to its surroundings, to its electronic structure, basically surroundings. But what happens during high temperature synthesis, why there are vacancies formed? This question is, I think.
But I think there are two equivalent positions and you have one iron.
But still there are vacancies. Still this is not stoichiometric. I mean, you have a small amount of iron always absent. Always absent. In our simulations, we still worked with Fe5, but I mean, the vacancies are, we define a little bit different way. We don't have a really iron deficient sample here. We have occupation, which we have distributed occupation, but in real experimental samples, we have real deficiency of iron, maybe 4% or something is always. You can, if you are careful, or if you've done the synthesis in a different way, you can get 2%. But still, everywhere in all the papers I have seen, some iron atoms are missing. Now, this is, I don't know, I mean, this is really experimental, careful. Yes, please.
In this system, the last one, the iron movement is in the AB plane, right? When you apply magnetic field in the AB plane, large magnetization.
There was in this M versus T plot, I think.
The size of the iron. And if you remember, M was isothermal magnet samples. What is the saturation magnetization? condition that you get when you apply field along it in the AB plane. I can also show you.
You are asking me experimentally.
I mean, in this paper, if they must have done a magnetic field.
Yeah.
Do
Absolutely.
you have any idea what the saturation movement is like? What is the size of the iron movement?
I think it's in one paper it was reported in a range 0.8 to 2.5 Bohr magnetons. That was the range, and when we calculated that, it can be seen from the M versus T curves here at T equal to 0 Kelvin here. If you just follow these here, so 2.5 Bohr magneton for this species, then around 2 Bohr magneton, then around 1.75 magneton, then around 1 Bohr magneton. So there is a huge variation of iron moments per site actually. So this more or less matches with the experimental report that is a range of magnetic moments is available.
But can I have a very quick question?
Oh, yeah, sure, go ahead.
So, what is the iron distance compared to the iron distance in iron metal?
Iron distance in.
Because I'm also curious, like others, about the exchange mechanism.
It's a good question.
Because diagonal interactions
Oh.
are rather too small to explain anything at Curie temperature, which is of the order.
I think it's RKQY type of interaction, but the closest distance, what you ask, I think that is of the order of similar distance as in metallic iron, which is 2.49 angstrom. Yeah, I mean that. It's direct exchange. So some of the iron atom, some of the exchange interactions are direct exchange that you can show from different mechanisms, but I think it does not tell us about the indirect exchange interactions, which most probably is RKKY type of interaction, which is a long range interaction. So now how exactly this RKKY exchange interaction takes place, that is a question I think one should try to understand. Because you have other like germanium atoms in between and things like that. So it could be that there is some kind of peculiar exchange mechanisms, indirect exchange mechanism. But I believe that some modified RKQI is responsible for that. Apart from direct exchange, which is happening for the closest iron atoms. Yeah.
Would there be DMI?
It will be DMI. We have calculated DMI. We see for some species the DMI interactions are significant, but we don't know what is the consequence of that, because the Curie temperature is not influenced by the DMI, because these are much smaller effects. But some other subtle magnetic textures that can be influenced by that DMI.
You talked about some skyrmions.
Yeah. But it is not very clear where the skyrmions are coming from, because people even say that iron oxide formation can give rise to skyrmions. Some papers, and sometimes in the van der Waals gap, iron interstitials go and they can form skyrmions also. So that is a difficult thing. Yeah.
So if there is no other question, it is time to Biplab once again.
Thank you very much.
Thank you.